let me start by introducing myself. I am Oodler online. The name doesn't really mean anything. That's just my name online. So, shameless plug for some of my fun modules and real modules there. This is my GitHub if you want to check those things out. Normally, what I do is I do OpenMP things or storm surge modeling things, but here I'm going to be talking about something that is totally out of my depth by this brilliant person, Dr. John P. Linderman, who contributed the initial qsort algorithm to the Perl binary. I guess I really didn't do enough background information on him, so I wish I could have given the history of the sorting algorithm in Perl. But this gentleman popped his head up, I guess, a few years ago on P5P when they were talking about removing the qsort implementation. And I contacted him because he seemed like a interesting person and it seemed of historical significance. So we started chatting, and he talked to me about some of his ongoing research. He is retired, as you can see on his GitHub page, but he worked at Bell Labs at AT&T and was around all of those Unix legends and contributed quite a bit of things himself. And in fact, I don't know, can y'all see this this book? It's the Awk programming language book that I like collecting old computer books, and I happen to notice this one is from 1988, and Dr. Linderman is mentioned in the acknowledgments um, on this page right here. The page 6, Roman numeral 6 of the prefix or the preface. So he was definitely working with these individuals, the individuals for whom Awk is named, their initials, and he contributed quite a bit, I'm sure, uncredited and also credited. So I'm going to be reading some a paper from him that he discusses some results, new results of the qsort algorithm. I am doing this because I think it is very interesting and of historical significance. However, I cannot claim that I'm really going to understand a whole lot of what he's saying, but it is related to Perl, and feel free to ask me questions, but hopefully you will find this as interesting as I do. So, without further ado, I will proceed. Now, this is from Dr. Linderman, and so when I read I, that's actually him, and then he does mention me shortly into this, um, but I'm going to be speaking in the third person. So, I will begin. Historical background. Decades ago, I ported Peter McElroy's optimistic merge sort to Perl, and this is P mom is a reference, and I have it pulled up actually here. One of these right here. It's optimistic from optimistic sorting and information theoretic complexity. So I will be providing links to these references in the aftermath of this talk. So he ported this optimistic merge sort to Perl. It coexisted with, rather than replace, a quick sort written by Tom Horsley. Peter's sort was generally faster than Horsley's sort, was stable, and could not go quadratic, as the Horsley sort could be made to do on organ, pipe, or sawtooth input. So the Perl porters were happy to use merge sort as the default sort. However, some users reported that Horsley's sort was faster, so it was retained. It should have looked in. I should have looked into these claims, but I did not. My guess now is that they involved sorting data with many duplicated keys, for which qsort has some significant advantages. When I learned of Bentley McElroy's qsort, BMQ, which is this paper here, engineering a sort function, here and after abbreviated as BMQ, I thought a variant it might make a worthy replacement for Perl's Horsley sort, qsort, being faster and less likely to go quadratic. In 2017, qsort was removed from Perl. BMQ had only recently come to my attention, and I hadn't spent a lot of time thinking why any qsort implementation was worth retaining. I puttered around with variants of BMQ for a while in 2008 and 2019, but without an obvious place for it in Perl, I turned my attention elsewhere. In the spring of 2021, Brett Estrade responded to a posting of mine in the Perl Porter's Digest, bemoaning the removal of qsort. He said he might have the chops to get it reconsidered for inclusion, or at least make it available as an optional package. This rekindled my interest in working on a pointer-based qsort. And I should point out I do not have the chops for this, and I may have indicated I did or had some false confidence in the past, but I don't have the chops to do this. Okay, maybe after studying it for a few weeks, but it's heady stuff. Okay, so what is pointer-based qsort? The standard Unix system qsort routine, of which BMQ is a popular implementation, sorts arrays of elements of fixed size using a comparison routine supplied by the user to determine how two elements should be ordered. In Perl, the elements being compared, which we'll just refer to simply as keys, are seldom of uniform size. In fact, the act of comparing two such keys can cause their size to change. For example, a key that starts out as an integer may grow to include a stringified representation of that integer if it participates in a string comparison. This presents no particular problem for the standard qsort since it can sort pointers, all of which have the same size, to the keys that will determine sort order. But there are good reasons to define a sorting routine that only sorts pointers, even though this disqualifies it as a drop-in implementation for the system qsort. Although BMQ does an admirable job of accommodating keys of any size, swapping two keys will depend on their size. As such, the number of swaps can significantly impact overall performance. Swapping two pointers or copying a pointer from one place to another is a very low overhead operation with no serious performance implications. Um, let me
look over here.
All right. Okay. Sorry about that. If BMQ wanted a place for an extra key, like a reserved place for the pivot element, it would have to allocate it dynamically. Space for any fixed number of pointers can easily be provided as part of automatic storage, leaving allocation and deallocation to the compiler. In a similar vein, allocating space for a parallel copy of pointers is less scary than allocating space for another copy of possibly large elements. The availability of a spare copy makes it easy to guarantee stability, the preservation of the original order of input elements, and space to generalize how many rounds of median of 3 will be involved in the selection of the pivot element. My implementation always assume the existence of a parallel array of pointers, which is already assumed by the Perl merge sort implementation.
Perl has just merged into your sorting.
In fairness, memory on modern computers is often cheap and plentiful. I have implemented versions of BMQ that allocate space for a separate copy of the input array, and they enjoy many of the same advantages. Okay, section 3, a quick aside about repeated keys. The number of distinct keys, k, is substantially smaller than the number of elements, n, then the expected number of comparisons done by any qsort implementation with a fat pivot collecting all keys equals to the pivot. Looks more like n log k than n log n. At each partitioning, all equal keys are gathered in one or the other of the partitions induced by the pivot, or end up with the pivot to which they are equal. That means that the number of keys in each subpartition is roughly half, resulting in n log k behavior. That's more What's more, the keys equal to the pivot are put where they belong and never again participate in recursive calls. When keys are essentially unique, putting one key where it belongs and ignoring it thereafter doesn't matter much. It can matter a lot if n over k is large. These two features are not shared by insert sort or merge sort or any commonly used comparison sort of which I am aware. Peter's merge sort benefits some from repeated keys, as longer and longer runs of repeated keys can result in sublinear merging. But the keys aren't taken out of circulation altogether, and the number of merge passes still looks like log n. Are repeated keys common? Consider sorting by US telephone number area codes, of which there are no more than 1,000, or by the leading 3 digits of US zip codes, which are highly geographic, or entire 5 digit zip codes, which are even more geographically refined, or on the dates in a 5 year span of dates. Repeated keys will often occur in real-world sorting applications, and a sort that gets a big performance boost from such data is worth considering. Section 4, extending the Bentley-McElroy qsort. Although the exact nature of the pointer-based qsort, hereinafter abbreviated as PBQ, has changed over time, its basic structure is a straightforward extension of BMQ. It assumes that it is sorting an array of pointers to elements that may or may not be of the same length. Since the size of pointers is known, there is no need to specify the size of the things being sorted, as is needed for BMQ. The user-supplied comparison routine should assume it is passed the address of two elements, not the address of pointers to those elements, even though it is the array of pointers that is being sorted. PBQ assumes the availability of a pointer array of the same size as the array being sorted. This auxiliary array is used to make PBQ stable in a way to be described, and as an area in which to conduct multiple rounds median of 3 competitions. The ultimate winner being used as the pivot element about which partitioning is done. This generalizes the BMQ concept of using 0, 1, or 2 rounds of median of 3 to choose the pivot. Like BMQ, if a partition has size n, originally the size of array to be sorted, small partitions are sorted in place using insertion sort, which is stable. Larger partitions are sorted by choosing a pivot element somewhere in the partition, then forming 2 strictly smaller partitions, those comparing low to the pivot and those comparing high to the pivot. We'll simply say less than or greater than, rather than speaking about how the comparison routine orders its arguments. All lesser elements are gathered at the left end of the partition, followed by all the equal elements with the greater elements at the right end. This leaves the equal elements where they belong, and the partitions at the left and right ends are sorted recursively. Where BMQ reorganizes the original partition by swapping elements in place, PBQ employs the auxiliary array. The elements of the original array are compared in order to the pivot element. Low elements are packed together at the left end of the original array. High elements are packed together in their original order at the left end of the auxiliary array. Equal elements are packed together in reverse order of appearance at the right end of the original array. When all elements have been assigned their proper place, the equal elements are added following the low element back into the original array. They are added right to left from the auxiliary array, thereby restoring their original order of appearance. The high elements follow the equal elements left to right in the same order in which they appear. As in BMQ, the lesser and greater elements are then sorted recursively. As John Bentley said, the algorithm is so simple that even JPL couldn't get it wrong. JPL is Dr. Linderman's. No, JPL is Dr. John P.
Linderman, that's funny.
He signs his emails JPL. So yeah, but also
JPL means the Jet Propulsion Lab.
Yeah.
That's what everybody else knows it as.
So
That's
just
funny.
to clarify, the
It's like
JPL,
calling yourself NASA.
he's-
my initials are NASA, so I just call myself NASA.
he's a very, very humble and self-deprecating guy.
But he's super smart.
Super smart. Yes. Okay. Other ways to stabilize qsort. That is John, don't know if the use of an auxiliary array to stabilize qsort was previously described. It seems obvious enough that it probably was, but the influence of the original qsort interface, where the elements might have been of any size as long as they were all the same, seems to have predisposed people against making a spare copy. Instead, the most common suggestion for stabilizing using space proportional to the number of elements being sorted is to create an array of indexes and sort the indexes based on the elements at those indexes, possibly, with ties being broken by comparing the indexes themselves. I did something like this to stabilize the Horsley Perl qsort, but it is a terrible approach for at least two reasons. For one, having sorted the indexes in the order induced by the corresponding elements, if you want to arrange the elements in the proper sorted order, you have to descramble them. This is doable but not worth describing because the even more terrible part of the approach is that breaking ties based on index means there are no two elements that compare equal. This negates the potentially huge performance gain qsort offers. Our algorithm still recognizes equal keys, thereby preserving the advantage qsort has when there are many duplicated keys. Comparing sorts. I apologize for wandering deep into the weeds here. It is necessary or at least useful for motivating my emphasis on memory caches. I have a suite of tests that measure the runtime of various sort implementations on exactly the same inputs. The inputs are initially generated by a program that takes three arguments: the least non-negative number allowed, the greatest non-negative number allowed, and the total number of samples to generate. Samples are generated by picking a number in the range specified by the first two arguments using a uniform random generator. I store these numbers in a file called u least greatest x sample, where the u indicates the samples are chosen using a uniform sampling technique over the indicated range. For example, the 10 million lines in file u1 10x 1 million might include 6, 4, 4, 10, 2. Duplicates must occur if the number of samples exceeds the range, and probably will occur even if the vast range vastly exceeds the number of samples. There is no way to force the generator to avoid duplicates. The numbers are originally stored in a dynamically growing array of native unsigned integers. The test suite does not interpret the name of the file from which it reads numbers. The name is a mnemonic for human consumption. The test suite keeps track of the largest value seen and the total number of samples seen. This enables the test suite to construct an array of fixed length strings that encode a right justified non-negative integer sample value followed by a right justified tag in the range 0 to, not through, not through the number of samples, so the sorted results can be checked for stability. The array of fixed length strings and fixed length tags could have been created on the fly from the same arguments used to create the file, but there are several good reasons to capture them in a file. By far, the most important is the need to reproduce exactly the same inputs that expose buggy behavior. Then, after modifying a program, it is possible to verify that the bug has truly been eliminated. Another reason is to make it possible to test code on a different machine without making assumptions about the random number generation on that machine. By simply copying a file, we are assured that the same inputs will be seen. The samples and tags could have been stored as native unsigned integers, saving both space and comparison time. I wanted to be able to tweak the length of the strings being compared as a way to slow down or speed up comparison. I now believe this was misguided, but I'm glad I did it because it exposed some unusual behavior that needed explaining. The file can be used to ensure that all sorts see exactly the same integer values and to confirm consistent performance over multiple runs. Early tests at least all generate 10 million samples. This was done to force the sorts to run long enough to generate meaningful runtimes. It is almost certainly not representative of the size of typical sort inputs. This may distort the performance measurements, although since most of the activity takes place on smaller and smaller partitions, there's reason to believe that the performance measurements are representative. After reading in and creating the array of elements and tags, a testing program sorts the arrays using a number of precompiled sorting routines. A test against a particular routine looks something like the following. A pointer array is initialized to address the array of elements and tags. A global comparison counter that is incremented by the comparison routine each time it is called is initialized to 0. A timer is started. The sort routine is invoked on the array of pointers. The timer is stopped and comparison count is saved. The sorted results are checked for correctness. A summary is produced. The summary produced for a few of the particular sort routines might look something like the following. And I will just let you soak that in. For each routine, the file from which the input was derived and a name identifying the routine is printed, followed by comparison and element counts, and the way the elements are structured. Key length and tag length. Finally, instabilities, disorders, and runtimes are displayed. Instabilities equal keys whose tags do not appear in strictly increasing order are to be expected for in-place qsort routines, but not for stable routines. Disorder would indicate a bug for any routine. No special care was taken to maximize repeatability of runtimes other than using a command task set to prevent routines migrating from processor to processor. In particular, tests were not run single user. To confirm that runtimes were meaningful, the same tests were run multiple times, and the outputs were summarized for each input file. First by decreasing order of comparison counts, then by decreasing order of runtimes. Comparison counts did not change from test to test for most of the routines because they did not introduce any randomness. The exception was the Horsley Perl qsort, which I long ago modified to scramble the original inputs for a large partition to make it difficult to feed it inputs that could induce quadratic behavior. This certainly did no favors for the performance on the arrays actually sorted. Run times are reported based on averages, along with population variances. A portion of the summaries follows. And here are the results of the test program that he described above. The tiny variances in runtime in parentheses suggest that times were largely repeatable. Memory caches. I am not a hardware person. Most of what I know about cache memory I learned from a blog by Igor Ostrovsky, A Gallery of Processor Cache Effects. It seems like an interesting thing to check out. It's a good read and I recommend it. Brett will provide this link later. I, John, cannot pretend to understand a sort runtime performance without considering the impact of memory caches. Sorting elements versus pointers. Since the sort keys being pointed to are themselves of uniform fixed length, the original BMQ sort can sort the elements themselves rather than pointers to the elements. Swapping pointers has very low overhead. Swapping elements, particularly when their length and alignment forces byte at a time swapping, seems very clumsy. But if you look at the performance ranked results over multiple tests, here, the BMQ sort on elements, original or stabilized, is consistently the top performer. This is first line right here. This makes sense if you take memory caches into consideration. The pointer-based qsorts will pack the pointers into smaller and smaller partitions that will fit in faster and faster caches. Visiting these pointers in order will become very efficient, but the elements to which they point remain scattered about in memory, benefiting very little from memory caches. Sorting the elements themselves packs them together into smaller and smaller partitions, faster and faster caches. When you visit one element, you may well cause the next element to be loaded into fast cache, greatly reducing the time to access it. This might be an opportune time to note that comparison counts are a poor proxy for performance. Merge sort often is a standout in terms of comparisons, but is reliably outperformed by qsort variants. Element, length, and runtime. While we have at hand the performance results showing the superiority of sorting elements over sorting pointers, consider the following anomaly. Elements from U1 10 million times 10 million have 8-byte keys and 7-byte tags. Although 10 million was an allowed value, it apparently didn't appear. So the maximum key length was only 8. Elements from file U0 9,999,000. Well, you can read it.
No, I want to hear the whole thing.
Nine. Wait, let
How
me.
many nines are there? Just tell us how many nines.
There are
1999.
There are 9
I remember
nines.
1999.
There are 9 nines.
That is nine-tastic. 9!
So the elements from the 9 nines times 10 million have 9-byte keys and 9-byte tags. Keys from the first file take at most 8 bytes to resolve the sense of comparisons, while those from the second take at most 9 bytes. So it would make sense that the longer keys would slow things down. The timing results show the exact opposite. The longer keys sort faster and by a significant amount. The number of comparisons is relatively close, so what's going on? Dynamically allocated storage into which the elements are packed is typically allocated so that native constructs like pointers and double precision floating point numbers would be properly aligned. This often implies that storage is aligned on a 16-byte boundary. When 16-byte elements are packed together, the 16-byte alignment of each element is preserved. When an address in memory is loaded into a 16 bytes cache line, a size common to many architectures, the cache line is loaded starting at the 64-byte boundary prior to the address. A 16-byte element might end up at the start of the cache line or at offset 16, 32, or 48. But no matter where it lands in the cache, the entire element fits in the cache. When 15-byte elements are packed together, their starting addresses will not be so nicely aligned. 15 and 64 being relatively prime, a 15-byte element will be equally likely to start at any of the 64 offsets in a 64-byte cache line. If it starts at any of the last 6 offsets, the last byte of the 7-byte sort key will not be in the cache line. This won't matter if the sense of a comparison is resolved by the bytes in the cache line, but it will require another cache line load if the sense has not been resolved. And as partitioning brings nearly equal elements closer together, more bytes will be necessary to establish the sense of comparisons. My dream of using key lengths as a way to fine-tune the expensive comparisons was completely obliterated by the impact of memory caches. It still might be possible to observe the effects of key length on performance, but only if overall element length is controlled to mitigate caching effects. Shouldn't stability cost extra? One final look at the performance ranked results on the file U0 9 nines times 10 million. As usual, sorting on elements rather than pointers tops the list. But third and fourth place here goes to stable qsort. Fifth and sixth places go to unstable in-place qsort, both modified to know they are sorting pointers. In a sense, unstable qsorts should have an easier job. A stable sort must find the unique permutation of inputs that result in stable sorted order, whereas unstable sorts need only find a permutation that correctly orders distinct keys regardless of input order. The explanation, I believe, is the way that pointers to the elements are initialized. Adjacent pointers address adjacent elements. In the first partitioning pass, both BMQ and PBQ start at the left end of the partition, comparing pointers to the elements in the pivot. If the element compares low or equal, BMQ eventually compares the element at the next pointer to the pivot. Since the element addressed by the next pointer is adjacent to the element addressed by the previous pointer, it may well already be cached, making it much faster to access. If the element compares high, BMQ starts looking backward from the end of the partition for an element that compares low to swap with the one that was high. The element pointed to is very unlikely to be in a fast cache, but as long as high or equal elements continue to be found, they tend to prime the cache for the next element that will be referenced. When a low element is encountered, the pointers to it and the elements from the left end are swapped. This introduces a discontinuity in both partitions. The elements addressed by these pointers are no longer near the elements originally addressed. In this way, BMQ tends to shuffle the pointers so that a sequential pass through the pointers is a partition ceases to be a sequential pass through the corresponding elements. By contrast, PBQ visits all pointers in order. On the first partitioning, it therefore visits all elements in order, perfect for pre-caching elements. Pointers to elements that do not compare low will be moved to the high or equal partitions, so gaps may appear between neighboring pointers. But pointers to elements far removed are never interposed. Sequential passes through pointers always correspond to elements at increasing addresses. Fetching an element always improves the odds of prefetching the next element to be addressed. I believe this explains why stable sorts have an advantage when pointers and elements are arranged in this way. My initial impulse was to think that this invalidated all the test results, but on second thought, it isn't completely unfair. An external sort like bin sort often reads lines to be sorted into one end of memory and addresses them in an array of pointers from the other end of memory, essentially the same as the way the test data was arranged. So it is not a contrived situation. And if stability confers an advantage, that's a feature, not a bug. But it means a different testing regime should be also considered. And that is the end, sad to say. Um, and I will, I guess, turn it over to questions.
Okay, yes, I do have a few questions. First of all, we had several people that have been joining, so
Very good.
I'll unmute myself here. Welcome to everyone that's been joining. Thank you so much, everyone. And on behalf of those who have just joined, can you please give a brief overview again of what the main point of this paper was? Because a lot of them came halfway through.
Yes. Okay. So a gentleman named John P. Linderman,
Yes.
JPL, not the Jet Propulsion
Not the
Laboratory.
jet, although it's the same brain power.
Same brain power. He, as you can see in his GitHub profile, MIT. He got his bachelor's in math in 1968. I guess that's his master's in CS in 1970. PhD in CS in 1973. Also from, I guess all of them from MIT. But he was a programmer at Bell Labs AT&T from 1973 to 2012 and specialized in C and Perl, which means that he was around when Unix was being developed and basically during the heyday of Bell Labs. And
Very exciting.
very exciting.
I mean, if I could go back to one point in computer history, that might actually be it.
I would definitely be a fly on that wall.
That'd be at the top of the
I
list.
would work as a janitor there.
I would totally be a janitor
Like-
there.
But not a Goodwill Hunting.
The janitors there are probably smarter than all of us now just because what they were hanging around at the time.
Absolutely. And so, well, I guess a few years back on the P5P email list, they were discussing removing qsort, and I saw Dr. Linderman speak up, and I guess I saw that he had made the first implementation for Perl's sort using qsort. I don't know, I can't guess the day, but we'll just say back in the day. And of course, he specialized in this. This is one of the algorithms he specialized in at Bell Labs. And so I contacted him, and thought maybe I could take what he had done and put it in a Perl module. And that never happened, and I certainly don't have the skills, I think, to do that. At least not without a lot of hand holding. But we decided we started up a nice conversation back and forth, and I contacted him when we started up the Science Perl Journal and activities with the Perl community, and asked him if he would be interested in presenting some interesting results and some work that he had been doing that he shared with me. So the paper I have been reading is basically like a pretty, he calls them notes, but it's a pretty well developed discussion about the qsort algorithm that was implemented in Perl, the background of it, and then the some results that he got that I'm sure you, at least whoever came in late, may have heard of this. But this recording will be available, and we'll be able to you'll be able to see the whole thing. But it's very interesting. It's historical. It's computer science, and it's pretty interesting. One other thing I wanted to point out is Dr. Linderman is I guess everybody is familiar with what awk is, and this is a book from 1988, a reference guide, which I like to collect old computer books. And I was thumbing through this one day and noticed that Dr. Linderman is mentioned in this acknowledgement page. It's in the preface, Roman numeral, page 6. So that is the answer for that question. And then, Will, do you have any other questions?
Yes, I do have one other question. And it's another generic question. But I just wanted to sort of make sure that I understood. I'm gonna give back a very overview description of what I understand of this, and I just want you to tell me if I kind of get it correct. Okay. So historically speaking, there was the software called qsort, and that was put into Perl a long time ago. Back in the day.
Algorithm, yes.
It was an algorithm.
Yes.
And it was callable. It was either used by Perl internally, or was somehow callable by. Was it part of the sort command? Okay, so part of the sort command.
And it allowed you to give it as one of its input a comparison function.
Right. So because I remember that or at least I think I remember that the sort command has a heap sort implementation. Anyway, that's what I remember reading when I was reading about the Perl sorting function. Anyway, but yes, I do also recall that it's customizable in the sense that you can set several different possible sorting algorithms because they all have these different sort of behaviors. So then so then fast forward to 2021, you and he talked on the list.
Yes.
He wanted to find, it had been, 2017 or 18 or something. When did it get removed?
It got removed in 2017.
17.
Yes.
So then between 2017 to 2021, you contacted him or he contacted you, talked on the list in 2021 to try and get it back in again. And that was a little bit more difficult than just like, hey, let's reverse this thing because there's all sorts of, I assume it's both technical and political issues blocking any sort of reintegration of anything.
Right. And I contacted him thinking maybe I could offer it as a module. But that conversation really didn't go very far. What became the topic of the conversation was he got interested in looking into some work again regarding it, and that's the source of these notes. So again, me asking him about it rekindled his interest, and he was kind of like very focused on the very interesting investigation that we presented here.
So So he's comparing, so then in his investigation, he's comparing qsort with some other algorithms, and he goes kind of deep into what their behavior differences are and how they twiddle these, both the keys and the, what are they, references or
Yes, he was looking at the various algorithms that were being used, both sorting elements directly and also versus sorting pointers to the elements.
right, the pointers, right, and and then also talking about how Perl automatically inflates some data structures based off of comparison operators occurring.
Due to the stringification of things like
Stringification or nullification.
Yes.
Both, presumably.
Yes.
And overloading of scalar values with multiple types.
Yes.
And that in turn can affect the actual behavior of the sorting algorithms. And so it really becomes much more complicated than you would think sorting should be.
Right. And the surprising result he was discussing is that sorting the elements directly was faster was faster than sorting pointers because of the cache effects, the cache line effects of the modern CPUs.
Okay, so basically, old dogs can learn new tricks, or
Yes.
old tricks can learn new dogs.
Yes. Especially if you have cache.
Okay, so cache is king.
Cache is king always.
Okay, cache is king. Now I understand. That's the basis of all of reality. Okay, cache. Now this is a CACHE cache.
Yes.
Correct. Okay.
Not cash money.
Not cache. Well,
Not
that's
cache.
another type of
Cash Patel. No.
Cache me
Cache.
outside. Cache. Okay. Catch it. Well, that's good. Does anyone online? We have quite a few people who came in late, and I tried to kind of have a little discussion with Brett to review about this paper by Dr. Linderman. Does anybody have any questions about, in general, Perl sorting, qsort, or Dr. Linderman that we can maybe try and answer? Now would be a good time. You can unmute yourself, I guess. Get a question. Going once, going twice. Okay, well, I'm going to say thank you very much, Brett. And let's have a round of applause. Okay, great.